let's talk about open and closed tubes. They're really straightforward. I know they can seem a little scary. All right, let's start with an open tube. An open tube, okay, looks something like this. Now the simplest you can have, remember the wave has to touch the edges. All right, so it's going to come around like this. Bad diagram. So I have a length L. If you look at this is L is 1/2 of a wavelength. Now, what is the next harmonic going to look like? Same length. All right, you're going to pardon my sketching because it's got to go up, come down, and come back. All right, so I see L is, how much of a wavelength is this? This is one wavelength. So do you mind if I write this as 2/2 L lambda? Now, the third one's going to give us our formula. All right, so I need, well, not 2 nodes inside, but 3. All right, so up, down, up. Now you're going to do a much better you're going to do better at drawing these than me. How much is this? This is, oh no, 1. This is 2. How much of this is? This is 1 full one, and this is 3/4. 3/2 lambda, excuse me, not 3/4. So you see, if I were to solve this, the nth one would be L is n/2 lambda. So that if we solve for lambda, lambda is 2L/n, where n is 1, 2, 3, etc. Now I know the velocity is f lambda. So when I solve this for the frequencies, that's frequency is v over lambda. So when I look for fundamental frequencies, all right, when I plug in lambda, this is v over 2L times n. So the frequency for open tubes is NV over 2L. And N is 1, 2, 3, etc. This has all harmonics. Now, let's switch pin colors and let's come do closed tubes. For a closed tube, this is closed, this is open, okay? You have a node at the end, and so the fundamental L is equal to 1/4 of a wavelength. For a closed tube, you have to have a node at one end, and it has to be an antinode at the other end, where for an open tube, it had to be antinode, antinode. So let's look at the second one. You have a node, it's got to go up, and you've got to have an antinode at the end. And if you look at this, you'll see L is 3/4 of a wavelength. And if we look at our third one, this helps us really give us a pattern. Now you guys know I tend to draw my I draw my tubes as long as I need. So this is 1 whole one plus 2/3. So L is 5/4 of a wavelength. We're having to add a half of a wavelength each time. So this is 1/4 of a wavelength, 3/4 of a wavelength. Ooh, I guess I got carried away here. Sorry. This is actually 7/4. All right. Remember how I do it? I just kind of draw my wave, and I put my, and I try to draw it correctly. My pen's not working. Oh no! I know y'all are tired of hearing that. This is 1/4, 3/4, 5/4, 7/4, 9/4, 11/4, etc. So that for these, lambda is 4L over n, where n is 1, 3, 5, etc. It's odd. So the speed, let's see, do y'all mind if I erase this a little bit? It's kind of got carried away with my lines. Put it in red. So V is F lambda. So F is V over lambda which is V, divided by 4L over N, where N is odd. Now, I derive this every time I do it. I truly do not keep this memorized. Now, let's look at this problem. What are the first three harmonics if the length of a pipe is 2.5 meters, open at both ends? So give me a diagram. Here's my diagram. Open at one end, open at both ends. And you're going to do better than this, so let's start over. It happens. Don't be afraid to erase. All right, it's got to be, come down like this. A lot of you just make X's, it's okay. 1, let's see, open, it's got to come back up. 2, oh, the third one's always hard for me. Let's see, I need 1, 2, I need 3 dots. Those are my nodes. So, in both cases, in all three cases, V is 345 meters per second. So for the first one, L, well, for all of them, L is 2.45 meters. So for the first one, L is 1/2 of a wavelength. That tells me lambda is 2L. So, let's see, V is F lambda. So F is V over lambda. So for the first one, F is V over 2L, which is 345 divided by 2 times 2.45. Now, 345 divided by 2 divided by 2.45. Whoops, mess that up. Let's see, 345 divided by 2 divided by 1 divided by 2.45 gives me 70.408. So let's just call it 0.41 hertz. What about the second harmonic? Where, let's see, for this one, L is equal to lambda. So the frequency is V divided by L. So it's V, which is 345, divided by 2.45. So 345 divided by 2.45 gives me 140.816 hertz. Now let's look at this one. The third one, let's see. All right, that is what? That's 1/2 of wavelength. There's a whole wavelength. So here L is 3 lambda over 2. So lambda is 2L over 3. So the frequency is V divided by 2L divided by 3, so it's up here. So it's 3 times, the speed was 345, divided by 2 times 2.45. So 3 times 345 divided by 2 divided by 2.45 gives me 211.22 hertz. Now, what if it was closed? All right, tell you what, let's go back to our equation. Suppose it's closed. The fundamental, all right, L is lambda over 4. If I'm at my second harmonic, I truly don't keep this memorized for folks. Goes up, comes down. Here L is 3 lambda over 4. So that we get L is n lambda over 4, where n is odd. So that lambda is 4L over n, where n is 1, 3, 5, 7, etc. Now remember, V is F lambda. So F is V over lambda. So it's V divided by 4L times N. So the first three, for N equal 1, F1 is V times 1 divided by 4L. So it's 345 divided by 4 divided by, let's see, what was L? 2.45? Or 35.2 hertz. For N equals 3, F3 is V times 3 divided by 4L. So this one is, when you plug everything in, it's 345 times 3 divided by 4 times 2.45. And yes, you can do shortcuts here. This is fine. So this is 105.61 hertz. For N equal 5, F5 is 5V divided by 4L. So it's 5 times, let's see, what was V? 345 divided by 4 times 2.45. So you get a frequency of 176.02 hertz.